Talofa everyone. In this video, we'll be looking at rates of reaction. This is good for Level 1 NCEA Science and Level 2 NCEA Chemistry. The first reason we might want to investigate reaction rates is that speeding up reactions is a really useful thing to do. And it is useful for many reasons, but most likely a cost reason, time reason, and to increase the yield of a substance. But there's also reasons for slowing down chemical reactions, and an obvious example of this can be seen in this apple. If we refrigerate our food, it slows down reactions that may spoil and decay food. To understand how a reaction takes place, we need to look at collision theory. On the left, we have reactants in white and red. In the middle, a collision, and on the right, we have new products, a rearrangement of the reactant particles. In order to successfully make products, the reactants have to collide. A collision that forms products is called effective or successful, and a collision must have sufficient energy, and the reactant particles must be in the correct orientation in order to be effective or successful, i.e., to form products. If we produced a graph of any chemical reaction showing how fast the products were produced over time, we would see that that graph started off very steeply, then it slowed down, the gradient lessening, and it eventually would become zero. Why is this happening? At the start, we have all reactant particles, so the chance of a successful collision occurring is quite high. And this means a lot of reactant particles are being converted to products every second. A little bit later, some of the reactants have already been converted to products, so therefore the rate slows down with fewer successful product-making collisions per second. And finally, at the end, all the reactants have been converted to products, so there is no reactant particles left to successfully collide, so the reaction rate is zero. Overall, you can see the steeper the gradient, the faster the reaction rate, which means the more successful product-making collisions are occurring every second. We started this video talking about how we could speed up or slow down reactions, and there are 4 ways that we can do this: concentration, temperature, surface area, or catalyst. We're going to spend a bit of time looking at each of these in turn now. Firstly, we need to know how we can measure the rate, and there's 2 ways we can do this. We can measure how fast the products are formed, for example, by collecting the gas that's made if a gas is formed as one of the products. Or, alternatively, we can investigate and measure how fast the reactants disappear. As you can see in the bottom picture on the scale, again, if we produce a gas, the gas will be released and the total mass will decrease over time. If we were to take the 2 previous ways of measuring and turn them into a graph, we would see the red line showing the products increasing if we were measuring the gas produced, and the blue line measuring the reactants decreasing over time. These 2 lines are in fact exactly opposite to each other, as the products appear at exactly the same rate as the reactants disappear, and you might be required to use either of these ways to discuss a reaction rate. Now let's take a look at concentration in detail. Here's a diagram of low concentration on the left and high concentration on the right. In a lower concentration, we have fewer particles in the same volume, and in higher concentration, we have more reactant particles in the same volume. If we have more reactant particles in the same volume, that means we've got more chance of a successful collision, and therefore a higher frequency of successful collisions, meaning a faster rate of reactions. Please note, the per volume and the per second are really important when discussing reaction rate and concentration. Let's now take a look at temperature. First of all, I want to show a graph here which has 2 reactions on it, a fast one and a slow one. Just a reminder that the steeper the gradient, the faster the reaction is taking place. The second point to note of this graph is that even though one is fast and one is slow, they both end at the same point. This tells us that they started with the same concentration and volume of reactants, meaning the same amount of products was produced, even though one was produced faster than the other. Now let's take a closer look at why one of those graphs was steeper and faster than the other. Obviously, we're looking at temperature. A lower temperature on the left in this diagram, the particles have less energy, and at a higher temperature, particles have more energy. An increased kinetic energy means the particles are moving faster in this case because their mass doesn't change. And this has two effects. Firstly, the particles moving faster collide more often, so there are more collisions in the same amount of time. And secondly, the particles with more kinetic energy have more energy to make the collisions more likely to be successful, remembering that collisions need a certain amount of energy to be successful. So there are two ways that temperature increases the reaction rate: more collisions, and the collisions have more energy. The next way to change the rate of reaction is by changing the surface area, and this only applies to a solid. As you can see, the solid on the left can be crushed or broken up into small pieces, which increases the surface area of the solid. And this means that there are more reactant particles exposed to react with, in this case, the green particles, the other reactant. And if there are more exposed reactant particles, there will be more collisions and therefore more successful collisions per second. So the key word here, exposed. The fourth and final way we can change the rate of reaction is to use a catalyst. As you can see here, the catalyst in yellow brings the materials, the reactants together, orients them correctly for a successful reaction to form the product on the right. The catalyst remains unused in the chemical reaction. This is about as much as you need for level 1, but for level 2 we need a little bit more information on catalysts. And we can put this together with our thermochemistry knowledge. Knowing what activation energy is, the catalyst provides an alternative path that has a lower activation energy than the reaction without the catalyst. This means more collisions have enough energy to collide successfully and form products. Therefore, there are more successful collisions per second and a faster reaction rate. It's important to note that the particles don't actually gain energy with a catalyst, but the catalyst somehow lowers the amount of energy required to make products or successfully react. And that's the end of this video. Catch you next time.